where I'll introduce the most widely used and most informative technique in electrochemistry, which is cyclic voltammetry. Okay, um, understanding this technique is not easy at all, right? Because this is the uh, dynamic technique. You keep changing the potential, okay, linearly from one point and then to the other point, and then you scan back to the original point, and then you scan again, again. Yeah? You can cycle the potential many times as you want, and then you measure the current. Okay, this is the cyclic voltammetry. Yeah? So, seemingly, the simple technique gives us a lot of information about the system. Okay, and when you scan positively, let's look at this voltammeter. In here, you scan from maybe a minus 1.5 volt down to minus maybe 2.5 volt. Okay, here you scan, and then uh, when you scan, starting from here, and this is typical voltammeter. Yeah? And then at this potential, the current, the y-axis is current begins to increase. Okay, since you scan negatively, this increased current is reduction current. Okay, something is undergoing a reduction here, and then after this passing this peak current, and then the current began to decrease, although you scan from further negatively. Okay, yeah. This current decrease. You have to have the deep knowledge of electrochemistry, but this one it depends on the diffusion. Okay, anyway, after passing this peak current, and then current began to decrease, and then here you scan back to the original potential, and then here, since you're scanning back, then you observe this the current of different direction. Since reduction takes place here, and then here scan back, this current observed current is oxidation current. Okay, this reduced species now begin to oxidize, yeah? And uh, now potential goes back to this original this potential. Okay, yeah? So uh, by looking at this current shape, okay, current shape, and then this potential position, okay, the peak potential position, okay, and the current magnitude, and then we can have some information about the system. Okay, let's first this one. This is the let me see. This current, yeah, this peak current is measured from here, yeah, to there. This is a peak cathodic current. Okay, and measuring the peak anodic current is not easy, since you uh, well, return the potential here. So you have to have a background current, and then here you follow this decrease in current, and then you extend. This is a dotted line is the extension of this one, and then from here you measure, vertically you measure the peak current. That is the peak anodic current. Okay, for the reversible case, peak cathodic current equals peak anodic current. If this is not the same, okay, and then something else must have happened. Okay, and if this peak anodic current is smaller than this one, yeah, like this one, yeah, and then we can assume that this reduced species undergoes not electrochemical reaction but other chemical reaction. Okay, that's why this peak anodic current is smaller than peak cathode current. Okay, and this peak potential also gives you some information. Okay, here, this one, this peak cathode current at the potential is called EPC. Okay, peak cathodic potential, and uh, on the returning scan, here is a peak. There is a peak anodic potential, yeah? EPC, EPA. Okay, and then this potential difference gives you information about the number of electrons here. Okay, here, and then for the ideal case, this difference is given by 57 divided by n millivolt. Okay, if there is only one electron, and then this peak potential difference is 57 millivolt. If there are two electrons involved, and then peak potential separation is half of this one. Okay, yeah, you understand? And there is a theory that dictates that peak current. Okay, for example, this peak cathode current is given by this equation. Wow, this is very complicated. Okay, IPC equals 2.69 times 10 to 8 n third n to 3 or second multiplied by this electrode area, and multiplied by concentration, and multiplied by this one uh, square root of diffusion coefficient. Yeah, this D is the diffusion coefficient, and also multiply by the uh, square root of a scan rate. Okay? The current is depends on the scan rate, how fast you scan the potential. Okay, but not directly proportional, but is proportional to the square root of a scan rate. So um, in order to obtain the 10 times higher current, you have to scan 100 times faster. Okay, because the square root of 100 is 10. All right, yeah. And then using this cyclic voltammetry, it is very easy to calculate diffusion coefficient of a species, right? Otherwise, measuring diffusion coefficient is not easy. Okay, but if the species undergoes uh, the electrochemical reaction like oxidation or reduction, using this equation, it is rather easy to calculate this D. Okay, so this cyclic voltammetry gives you a lot of information about the system. Okay? So that's why this cyclic voltammetry technique is widely used, right? And let's look at the cyclic voltammeter B here, right? While general shape is the same, yeah, it gives reduction and oxidation, but here the shape is different, because this one cathode peak and anode peak potentials are very widely separated. Yeah? That means that electron transfer is not faster. Okay, only from this voltammogram we can say that we don't know which reaction is like that, but that reaction electron transfer rate is quite slow. Okay, okay, and let's look at take a look at this molecule. This is C60. Okay, this is called the buckyball. Buck means the fluorine, and it has been discovered uh, maybe 30 years ago, and then the discoverer were awarded the Nobel Prize to the persons. Okay? And then one of the interesting thing about this one, it undergoes electron transfer. mm, It can take 6 electrons maximum. Okay, but more electrons, if you want, if you push more electrons into this molecule, and then this bond will be broken. Okay, so maximum 6 electrons this molecule takes. Okay, and then very interestingly, the 6 electrons are uh, you know uh, coming to this molecule, one by one. Let's look at this cyclic voltammogram here. Uh, 1 2 3 4 5 6, okay, and then returning. And also the injected electrons are removed from this molecule sequentially. 1 2 3 4 5 6. Wow, this is amazing. All right. Yeah. So this electrochemical property of this molecule is very easily studied by cyclic voltammetry. And then this one, uh, this low curve is the skew wave voltammetry, right? It gives the the uh, the peak shape voltammogram here, right? And also it gives 1 2 3 4 5 6 peaks, okay? And then this is more evident than CV, okay? And let's look at this gold cluster here, okay? Gold, number of atoms here, 147 gold atoms are here, okay? Then uh, this gold cluster undergoes many redox peak here, okay? How many? One, two, three, four, five. Yeah, okay, yeah, right. Many peaks. That means this gold cluster is the nano cluster, accept electrons sequentially one by one, and also it release electrons one by one here. How many peaks are here? 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. So 15 electrons are coming out of this cluster, okay, sequentially one by one here. One, okay. Otherwise, except electrochemical techniques, mm, there is no way to uh, what study the mm, electron transfer in and out of this cluster. Okay. Okay, but there are the electrode, very small electrode called microelectrodes. Okay, now look at that. This is the scanning electron microscope image of carbon fiber. This is carbon fiber at the center, embedded by Nafion. This Nafion is a polymer. Okay, this size is quite small. From here to there is a 40 micrometer size. Okay, very small. But this is another one. This at the center there is a electrode. The size is less than maybe about 5 micrometers. Very small. This is invisible with our naked eyes. Okay? This is all uh, mm, electron microscopic imaging. Okay, here this is I think even smaller. But you may ask why? Why do we need such a small electrodes? Right? These electrodes are difficult to make, but there is a big advantage of making a small electrode. Okay? There are many advantages, but one of the advantages is that since the electrode size is quite small, so this electrode can be inserted in a small area. Okay, even this electrode was inserted into the mouse brain to measure the dopamine concentration. Okay, you see. Let me see. Uh, this one, this Poltam, this response is the this C is amperometric traces from all 7 electrodes during exocytotic release of neurotransmitter dopamine. You see, the dopamine is a neurotransmitter. Hmm? It secreted from the brain, right? So if there's not enough concentration of dopamine, the Parkinson disease is related to this dopamine level. So it is important to measure this dopamine level. Yeah, and electrochemical method is a very strong, yeah, strong method. Okay? And I don't think the human brain there is a microelectrode experiment. No, I don't think so. But into the uh, mouse the brain, this small electrode is inserted to take the measurement of dopamine level. Okay, because this is dopamine is well, oxidized to this molecule. Okay, you see this part. This part is called catechol. Right? Catechol is the diol. Right? This is very well oxidized to this quinone. Okay, this is one of the usage of microelectrodes, right? In order to monitor the the direction in a very small area, and then you can use this microelectrodes. Okay. Okay. Now, so yeah, we reached the end of this chapter. Mm. The last topic is Carl Fisher titration of water. Okay. Uh, Sometimes it's important to determine the water concentration in a solvent. Okay, for example, many in organic chemistry use organic solvent, but sometimes that organic solvent must be very uh, high purity. Okay, and then usually organic solvent the impurity is water. Okay, so you have to remove the water, or you have to determine the water concentration in organic solvent, for example. And then how do we measure the water concentration very precisely? Yeah? So this Carl Fisher titration tells you the water concentration. Okay, the principle is not difficult to understand. Okay, you have to have alcohol and SO2 and base. Okay, and the base, the different bases can be used. Imidazole, what ethanol, amine. Those bases can be used. Okay, and then also you need to have iodine, and this species are all this one sulfonate group. Okay, and the principle is that, okay, now this alcohol react with SO2 and the base to give rise to this one. Okay, and then this species now react with water in the presence of iodine. Okay, gives this one. Okay? So here, look at this setup. This one, this part is the cathodic part, and the anodic part is here. Okay? And then anode solution contains this alcohol and SO2 and base and iodide. Okay, and then iodide to in order to what in order to use this reaction, you need to have iodine, not iodide. So iodine is generated at the anode by oxidizing this iodide here. Look at that. This is anode. Yeah, the solution contains. Let me see. Iodide, right? Yeah. And this is cathode. Yeah? By applying the potential at the anode, iodine is generated. Okay, and and this one more iodine. Okay, one more iodine now consumes one more water. Okay, you understand? This is electrochemical reaction, but actually you uh, apply potential, or you apply the current to generate iodine from iodide here. This is electrochemical reaction, and then immediately this iodine react with water with this species. Okay, in the presence of a base. All right, and then after all the water, yeah, in the solvent is consumed by iodine. Yeah, if there is no more water, and then this iodine now is ready to uh, be reduced to iodide, then here this iodine concentration is measured by another set of electrode here. This is the platinum electrode for biopotentiometric endpoint detection. Okay, you understand? Hmm? Like in coulometry, right? In the coulometry, uh, there there are two sets of electrode. Yeah? One is to generate some species, and the other one is uh, to determine the end point here. Okay, yeah. All right. So here is the end point detection, reaction. This is also there are two electrodes. One is anode and one is cathode. At the cathode, this one, the generated iodine, but actually there is a iodide, so the triiodide is there. Triiodide is reduced to iodide, and then at the anode here, anode iodide is oxidized to triiodide. Okay, so after uh, all the water molecules are reacted to iodine, and then still here uh, this anode still generates iodine because this solution contains iodide. Okay, and then iodine generated iodine, you know, cannot react with water because water already all consumed. Okay, and then this iodine uh, is in the form of triiodide is reduced to iodide. And then iodide is reoxidized. Okay, so current flows, much current here flows, and then you can stop when this current uh, increased over certain value. Okay, that's how this water molecule concentration is precisely determined by this Carl Fisher titration. Right, this is working quite well. Okay, this is end of chapter 16, and then you solve these problems and then upload in the eCampus. Okay, as you know, there is a solution available in the internet. Okay.